Hello everyone, I'm Vitalis. I'm an electrical and computer engineering undergraduate at the National and Technical University of Athens and a researcher at the Athens University of Economics and Business. Today, I'm going to present our work on Python call graph generation using a practical approach. This is a joint work with my co-authors, Theodoris Sotiropoulos, Panos Louridas, Diomidis Pinellis, and Dimitris Mitropoulos. Call graphs are directed graphs where nodes correspond to functions and edges denote calling relationships between them. They are very useful for profiling, dependency analysis, tool-supported refactoring, and many more. Generating call graphs for Python programs is not an easy task. Python has support for higher-order functions, is an object-oriented language with a dynamic type system, and in Python, class and function definitions can be nested, while in a typical use case, a module imports many other modules. Despite Python's popularity, there have not been many approaches for its call graph generation, in contrast with other languages, such as C, Java, and JavaScript. To address the aforementioned challenges, we have implemented PyCG, a static, interprocedural, and context-insensitive analyzer that can handle most of Python's features, including higher-order functions, classes, generators, and many more. PyCG works as follows. First, it converts Python source code into an intermediate representation containing expressions, definitions, and objects. Note that definitions are identifiers inside the Python program along with their type, for example, a variable identifier or a function identifier, while objects uniquely identify definitions via their namespace. PyCG evaluates the expressions of the intermediate representation using simple rules that we have created for each one of Python's functionality. These rules work by retrieving the current state and updating it accordingly. The state is the structure that contains the domains of the analysis, those being the current namespace, the scope, the class hierarchy, and the assignment graph. The scope can be conceptually visualized as a tree, where nodes correspond to definitions and their children are the definitions that are directly defined inside of them. It is very useful for distinguishing definitions through their identifier based on the current namespace. The class hierarchy allows us to handle Python's object-oriented nature. It represents the inheritance relationships among classes and is very useful for resolving class attributes and methods with respect to Python's method resolution order. The assignment graph is the structure that allows us to handle higher-order functions. It is a directed graph where nodes correspond to objects and edges denote assignment relationships between them. As an assignment, we treat assignments made through the equals operator, through function parameters, and return values. As an example, consider the assignment graph of the crypto module shown on the top right. The crypto module defines a class named crypto, which has an initializer and an apply method. The apply method takes as a parameter a higher order function that it applies to a string. Finally, the crypto class is instantiated and encrypts and decrypts a hello world message using the encrypt and decrypt functions which are defined in another external module. First, notice that this assignment leads to an edge being created from the CRP variable to the namespace of the crypto class. And in this case, the invocation of the apply method leads to an edge being created from its func parameter to the functions encrypt and decrypt. This will later allow us to resolve that a call using the func parameter will lead to the invocation of the encrypt and decrypt functions. And in this case, the encrypted and decrypted variables are assigned to the return value of the apply method. PyCG applies the rules of the analysis until the state converges. After converges, it iterates the intermediate representation one last time, reducing expressions into function calls. Then, using the assignment graph and the simple DFS operation, PyCG identifies all the possible functions that the callee object may point to, and adds call edges to them stemming from the current namespace. Moving on to the evaluation, we have implemented a micro and a macro benchmark and compared PyCG with two other static and open source approaches, namely Pyan and Depends. The micro benchmark contains 112 minimal test cases, which are split into 16 different categories. Each one of those test cases contains Python source code along with its call graph and aims to test a very specific functionality of Python. Note that this benchmark can also be used to evaluate future Python call graph generators. This table lists the results for the micro benchmark evaluation. We compare the tools in terms of completeness, meaning no false positives, and soundness, meaning no false negatives. Note that Depends is not included in this table because it is unsound in all cases, since it does not capture calls from module namespaces, and complete in all but two of the test cases due to its conservative nature. The results for PyCG show that it produces a complete call graph in all but one of the test cases and a sound one in 103 of the tests, while Pyan ranks lower in both metrics. This is due to Pyan not supporting some common Python features, such as higher order functions, or its limited support for other ones, for example, Python's classes. To evaluate our approach on real-world Python packages, we have implemented a macro benchmark consisting of 5 popular and medium-sized packages which we collected from GitHub. Since there is no acceptable implementation for Python call graph generation, we have opted to manually generate their call graphs, spending around 10 hours per project. This table lists the results of the macro benchmark evaluation. We compare the three tools in terms of precision and recall. PyCG produces a very high precision of 99.2% and is closely followed by Depends. And in terms of recall, PyCG has a 3.4 multiplier boost over the next best result with 69.9% recall. The lower marks for Pyan and Depends are due to them not supporting some common Python features, such as higher order functions, or their limited support for other ones, such as Python's object-oriented nature. In terms of time and memory, PyCG takes double the time as Pyan and consumes the most memory out of the three tools. That is expected because PyCG performs a fixed point iteration over the analysis state, while it maintains more information about the input Python program. Now, we will present a real-world case study on the fine-grained tracking of vulnerable dependencies. GitHub maintains a security advisor database containing vulnerabilities of packages and checks whether the repositories that it hosts depend on a vulnerable package version, and if that's the case, they notify the repository's owners about the vulnerability. However, a dependent might not have an execution path to the vulnerable part of the external package. In order to find out, we investigated PyYAML with the CVE that you see in your screens. We generated the call graphs for 106 of its dependents and checked whether there was an execution path to the vulnerable function named load. We found that this was the case for 42 of those packages, and therefore the rest might be considered safe. This concludes our presentation. In summary, we have introduced a context-insensitive and interprocedural analysis for Python call graph generation. We have created a micro and a macro benchmark and evaluated PyCG on those. The results showed that PyCG generates high-precision call graphs with adequate recall. Finally, we presented a real-world case study on dependency analysis. Thank you all for listening.
Hello. So I'm here with the authors of the paper PyCJ, Practical Call Graph Generation in Python. Congratulations for the work. So I have some questions in the chat. So Vitalis, the first question is from Hau. Does PyCJ identify and remove calls to procedures in unreachable parts of the code?
Okay. So first of all, hi everyone. Thank you so much for listening to this presentation. So to answer the question, PyCG outputs the call graph, and if a function is unreachable in the call graph, this can be directly found from the call graph itself. PyCG does not actually uh, uh, modify the input code, but further tools can use the generated call graph to modify the existing code and remove unreachable functions.
Okay, thanks for the answer, Vitalis. And Georgios Gosius has a question as well. How does PyCG deal with dynamic dispatch?
Okay, thanks for the question. And so when PyCG identifies a function, a method definition inside the class, then it traverses up the class hierarchy and finds whether functions with that same name have been methods with that same name have been defined. And if that's not the case, then PyCG adds an identifier, let's say a method identifier, and then adds an assignment edge to the function defined in the child class in the assignment graph. And using that, PyCG can identify function calls done via dynamic method dispatch.
Thank you for the answer, Vitalis. I have a further question from Ashwin. I have tried to run PyCG. I don't know if this is, let's see, directly on machine learning libraries such as NumPy, but ran into errors. Is it because of the way imports are handled in PyCG? In general, what do you think are the next steps to solve this such that it can be applied to large real-world libraries?
Okay, thanks for the question, and I'm very sorry to hear about the troubles that you had in running PyCG. So, it mostly depends on the error. So, I wouldn't call this a limitation. Uh, I wouldn't call this a limitation to running PyCG on large-scale libraries. It mostly has to do with the implementation, and we've tried to make a PyCG error resilient, but clearly something has slipped by. So maybe you could message me, and we could find out about the source of the error.
Hey, Florian has a question as well. Florian Ungermeyer. As far as understood, PyCG currently outputs JSON. Do you plan to extend your approach so that it can be easily visualized or offer some kind of visualization directly from PyCG?
Yeah, that would be a great feature. So um, currently, during this work, our focus was mainly on generating the call graph with the aim to generate call graphs for very large programs. So we didn't focus on the visualization aspects of it because, especially on large programs, a visualization wouldn't be of much help. But I believe it it is very straightforward to use the JSON output to generate a visualization using existing tools.
I have a follow-up just quickly. Have you tried to use the JSON as input to some visualization tool or no?
No, no, I wouldn't say.
Okay, it's just curiosity.
Mhm.
So we have a question now from Sridhar. Do you consider all dynamic information and calls? Does that not get into call graph explosion problem?
Let me just reread that again.
Okay.
Um, by I'm not sure I quite understand what Sridhar means by dynamic information and calls.
Let me jump to the next one. So
Mhm.
Sridhar, if you can clarify that, I can come back to the question after the question from Anders. So Anders has a question: is PyCG a whole program analyzer, or can it also produce call graphs for libraries without an application code?
Um, Again, I have some trouble understanding that question. So, PyCG can only generate call graphs for Python source code that it has access to. Is your question related to external libraries?
So I remember from the paper, Vitalis, that you have like some things that are you cannot, of course, create a call graph for the things that you don't have access to the code.
Mhm.
But I don't know if I can follow up on that, Anders. But for me, applications and libraries is a kind of application, I would say. I don't know what
I
you
would,
mean with applications versus libraries. If it's a user application or
I would say
uh,
the answer is yes. That
yes,
a
yeah.
library can be, PyCG can create a call graph for a library
Yeah,
Mhm.
so
Ah,
it's
standalone.
any software written in Python.
Hmm.
yeah.
Yeah.
PyCG can create call graphs for any software written in Python. We just need access to the source code.
Okay.
Mhm.
So Sridhar just clarified his question. If you consider all possibilities of paths and information at dynamic time, does
Mhm.
that get into a graph explosion problem?
Uh-huh. Okay. So, uh, PyCG tries to be somewhat conservative about its approach, and by conservative, we mean that uh, we store information that uh, we have quite some evidence that it exists. And the results on the micro benchmark showed that uh, there's not, I would say, not such a problem because PyCG can actually produces a very high precision call graphs. So we didn't find cases where uh, our approach outputted many false positives.
Okay, thank you. So Anders is clarifying that an application has a main method
Hmm.
and other entry points. So if this is a limitation of PyCG, so we need to.
No.
No.
Mhm.
Uh,
Okay, yeah, that would not be a problem at all.
Okay, let's try. We still have like 1 minute, 20 seconds. Let's see if we can get the last question from Ho. Restricted Python execution, where access to only specific functions and libraries is allowed, has been one of the hard to reach goals in Python because it's really hard to find out if restricted functions can be reached for a given code. Can PyCG help here? How much is the confidence that of PyCG if it does not find a path to the given function? That function cannot be reached.
That is a very great question.
Mm-hmm.
So, PyCG can help on that part since using the call graph we can find whether an execution path exists to a specific function, and if not, that function might not be reached. However, even though we have confidence that the output of PyCG uh, or contains facts that are mostly true. On some cases, it misses some facts, and the facts that it mostly misses are are related to mostly external functions and definitions as